What if I told you that there are places in our solar system where you could die in ways that would make even the most creative horror writer pause and reconsider their career choices? Places where the very act of breathing would turn your lungs into crystalline sculptures, where you'd be simultaneously crushed, frozen, and irradiated before your brain could even process what's happening. Tonight, we're embarking on a journey to every single moon in our solar system to explore what would happen if you found yourself dying on each one. And trust me, by the end of this series, you'll have a completely new appreciation for the gentle embrace of Earth's atmosphere and the warm hug of its magnetic field. But here's what makes this exploration truly fascinating. Each moon offers its own unique cocktail of death, its own signature way of ending human life. Some will kill you instantly with the mercy of speed. Others will drag out your demise in ways that stretch the boundaries of biological possibility. And a few, just a few, might surprise you with how almost hospitable they seem, until you realize they're playing a much longer, more insidious game. We're talking about over 200 natural satellites, each one a world unto itself, each one harboring its own specific methods of human termination. From the sulfur-spewing volcanoes of Io to the diamond rain of Neptune's moons, we're going to explore deaths so exotic they'd make alien filmmakers jealous. What you're about to discover will fundamentally change how you think about space exploration, about the fragility of human life, and about just how perfectly calibrated our home planet really is for our survival. Because when you understand all the ways the universe is actively trying to kill you, you start to see Earth not as a prison, but as a sanctuary. So settle in, take a deep breath of that beautiful oxygen-nitrogen mixture, and let's begin our morbid tour of the most deadly real estate in the solar system. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. By any chance, if your curiosity stretches beyond space and science, I would love to invite you all to visit and take a look at our new channel Boring Money, a place where finance slows down and fortune gently drifts in. I have dropped a link in the video description. Do consider checking it out. Let's start. Our journey starts close to home, with Earth's own moon, Luna. It's the most familiar celestial body in our night sky, the one we've actually visited, the one that seems almost mundane compared to the exotic worlds we'll explore later. But don't let that familiarity fool you. Our moon is perfectly capable of killing you, and it would do so with an efficiency that might surprise you. Picture this. You're standing on the lunar surface, somehow having survived the journey without a spacesuit. The first thing that would happen isn't what most people think. You wouldn't instantly freeze, despite the moon's surface temperatures ranging from 250 degrees Fahrenheit in sunlight to minus 250 degrees in shadow. You also wouldn't immediately explode like in the movies. The human body is remarkably resilient to vacuum, at least for the first few seconds. Instead, the saliva on your tongue would begin to boil, not from heat, but from the absence of atmospheric pressure. This is called ebulism, and it's one of the more unsettling ways that vacuum affects the human body. The water in your soft tissues would start to vaporize, causing you to swell up like a grotesque balloon version of yourself. But you'd remain conscious for about 15 seconds. 15 precious seconds to take in the alien landscape around you, to see Earth hanging in the black sky like a blue marble, to feel the strange sensation of your body betraying you in ways no human was ever meant to experience. Your lungs would be the real problem. If you tried to hold your breath, the expanding air in your lungs would rupture them from the inside. The smart move, counterintuitively, would be to exhale immediately and keep exhaling, letting the air escape rather than letting it tear you apart from within. After those 15 seconds of consciousness, you'd pass out from lack of oxygen. Your heart would continue beating for another minute or so, pumping blood through a cardiovascular system that was never designed to operate in vacuum. The blood in your veins wouldn't boil, contrary to popular belief, because your circulatory system maintains enough pressure to prevent that particular horror. Death would come from asphyxiation, typically within 1 to 2 minutes. It would be relatively peaceful as space deaths go. Your last conscious moments would be spent watching the most beautiful view any human has ever seen, the Earth rising over the lunar horizon before gently slipping into unconsciousness. But here's where the moon's specific environment adds its own macabre twist to your demise. Your body wouldn't decompose in any way we'd recognize on Earth. There are no bacteria in the vacuum of space, no atmospheric moisture, no oxygen to fuel the chemical reactions of decay. Instead, you'd become a perfectly preserved monument to human exploration, freeze-dried by the vacuum and alternately baked and frozen by the sun's unfiltered radiation. Over time, cosmic radiation would slowly break down the complex molecules in your tissues. But we're talking about processes that would take thousands or even millions of years. You'd become a lunar mummy, a testament to the moon's ability to preserve as well as destroy. The temperature extremes would play their own role in your posthumous existence. During the 2-week lunar day, when surface temperatures soar to 250 degrees Fahrenheit, your body would experience thermal expansion. During the equally long lunar night, when temperatures plummet to minus 250 degrees, you'd contract like a grotesque accordion. This constant cycle of expansion and contraction would eventually cause your preserved tissues to crack and fracture. But again, we're talking about processes that would unfold over geological timescales. The moon is patient with its dead. There's something almost poetic about dying on Luna. You'd be joining a very exclusive club of humans who have experienced death beyond Earth's protective embrace. Your atoms, forged in the hearts of ancient stars, would finally come to rest on another world, becoming part of the moon's own geological story. But as peaceful as lunar death might be, it pales in comparison to the creative ways that other moons in our solar system have devised to end human life. Because once we venture beyond Earth's immediate neighborhood, we encounter worlds where the very concepts of hot and cold, pressure and vacuum, solid and liquid, take on meanings that would stretch human comprehension to its breaking point. Let's travel outward to Mars and visit its two small moons, Phobos and Deimos. These aren't really moons in the traditional sense. They're more like captured asteroids, irregularly shaped chunks of rock and dust that orbit Mars in tight, fast orbits. Phobos, the larger of the two, is only about 14 miles across at its widest point. Deimos is even smaller, just 8 miles in diameter. Dying on Phobos would be a uniquely disorienting experience. The moon's gravity is so weak that you could literally jump off its surface and into space with a good running start. We're talking about a gravitational pull that's only about 1/1000th of Earth's. If you somehow found yourself on Phobos without a spacesuit, you'd face the same vacuum-related death as on Luna, but with the added surreal quality of knowing that every movement you made could potentially launch you into the void between worlds. The surface of Phobos is covered in a layer of loose dust and debris, the accumulated detritus of billions of years of meteorite impacts. This regolith, as scientists call it, would be the last thing you'd feel beneath your feet as consciousness faded. Fine particles of ancient rock and metal, each grain a tiny piece of solar system history, would cling to your body through electrostatic forces. But here's where its own unique twist Phobos offers on space death. The moon orbits Mars so closely that it's actually spiraling inward, doomed to crash into the planet in about 50 million years. So even in death, you'd be part of a celestial object that's itself dying, slowly succumbing to the inexorable pull of Martian gravity. Deimos, being even smaller and more distant from Mars, would offer an even more ethereal death experience. The escape velocity from Deimos is only about 12 miles per hour. That means a professional baseball pitcher could literally throw a ball off Deimos and into interplanetary space. Your death throes, the natural convulsions that accompany asphyxiation, could easily propel you away from the surface entirely. You might die not on Deimos, but floating in the space around it, your body becoming a tiny satellite of a satellite, orbiting the Martian system in an eccentric trajectory that would slowly decay over millennia. It's a death that would turn you into your own celestial object, a macabre piece of space debris with a very personal history. The Martian moons also present us with our first encounter with truly alien sunlight. The sun, as seen from the Martian system, appears only about half as large and bright as it does from Earth. Your final moments would be illuminated by a dimmer, more distant star, casting weaker shadows across surfaces that have never known the warmth of a thick atmosphere. But as exotic as dying on Mars's moons might be, they're still relatively familiar environments compared to what awaits us in the outer solar system. Because once we pass the asteroid belt and enter the realm of the gas giants, we encounter moons that redefine our understanding of what a world can be. Jupiter, the king of planets, commands a retinue of over 80 known moons. 4 of these, the Galilean moons, are worlds in their own right, each larger than Earth's moon, each harboring environments so extreme that they challenge our ability to even imagine what death would be like on their surfaces. Let's start with Io, Jupiter's innermost large moon, a world that makes hell look like a vacation resort. Io is the most volcanically active body in the solar system, with over 400 active volcanoes constantly reshaping its surface. The moon is literally turning itself inside out, spewing sulfur and sulfur dioxide into its thin atmosphere at velocities that would make a rocket engineer weep with envy. Landing on Io without protection would subject you to an environment so hostile that death would come not from one cause, but from a symphony of simultaneous biological failures. The surface temperature varies wildly from -300 degrees Fahrenheit in the polar regions to over 3,000 degrees Fahrenheit near active volcanic vents. That's hot enough to melt copper, hot enough to turn solid rock into glowing lava in seconds. But temperature would be the least of your problems. Io exists within Jupiter's intense radiation belt, bombarded constantly by charged particles accelerated to enormous energies by the giant planet's magnetic field. The radiation dose on Io's surface is about 36,000 times the lethal dose for humans. You'd receive a fatal dose of radiation in less than a minute, even if everything else about the environment was perfectly hospitable. The atmosphere, such as it is, consists primarily of sulfur dioxide gas, continuously replenished by volcanic outgassing. Breathing this would be like inhaling concentrated acid vapor. Your respiratory system would be chemically burned from the inside, even as the lack of oxygen caused you to suffocate. And then there are the volcanoes themselves. Io's volcanic plumes can reach heights of 300 miles above the surface, ejecting material at speeds of up to 3,000 feet per second. These aren't the relatively gentle lava flows we're familiar with on Earth. These are explosive eruptions that would make Mount Vesuvius look like a birthday candle. If you were unlucky enough to find yourself near one of these volcanic vents, Death would be instantaneous and complete. You'd be simultaneously flash frozen by the intense cold of space, incinerated by temperatures that exceed those found in steel foundries, irradiated by doses that would kill you dozens of times over, and chemically burned by an atmosphere that's essentially weaponized sulfur. But perhaps the most unsettling aspect of dying on Io would be the knowledge that your demise would be witnessed by one of the most beautiful sights in the solar system. Jupiter would dominate the sky, appearing 40 times larger than the Moon does from Earth, its swirling cloud bands and great red spot clearly visible to the naked eye. Your last sight would be of a world so magnificent that it would take your breath away, literally and figuratively. Your body would not rest peacefully on Io. The constant volcanic activity would eventually bury you under layers of sulfur snow and volcanic ash. But even this burial would be temporary. The Moon's surface is completely renewed every million years or so by volcanic activity. You'd become part of Io's endless cycle of destruction and renewal. Your atoms eventually incorporated into new volcanic eruptions, scattered across the Moon's surface in a geological reincarnation that would continue for billions of years. Moving outward from Io's volcanic hellscape, we encounter Europa, Jupiter's ice-covered moon that harbors one of the solar system's most tantalizing secrets. Beneath its pristine white surface lies an ocean that contains more water than all of Earth's oceans combined. But don't let this promise of liquid water fool you into thinking Europa would be a gentle place to die. Europa's surface is a frozen wasteland where temperatures hover around -370 degrees Fahrenheit. That's so cold that the very air you exhale would instantly crystallize and fall to the ground like microscopic snow. Your final breath would become a small pile of frozen water vapor at your feet, a poetic reminder of the warmth that once existed within your body. But the cold would be just the beginning of Europa's unique method of execution. The Moon's surface is constantly bombarded by Jupiter's intense radiation, creating a dose rate that would kill you in less than a day, even if you could somehow survive everything else. This radiation doesn't just damage your cells, it literally breaks apart the water molecules in the ice beneath your feet, creating a thin atmosphere of oxygen and hydrogen that you could never breathe. The surface itself tells a story of violence written in ice. Europa's crust is crisscrossed with massive fractures and ridges, evidence of the tidal forces that constantly flex and crack the Moon as it orbits Jupiter. These aren't gentle geological processes. The ice shifts and grinds with tremendous force, creating pressure ridges that tower hundreds of feet above the surrounding terrain. If you found yourself caught in one of these tidal flexing events, death would come from being crushed between moving walls of ice, each weighing millions of tons. Your body would be compressed instantly, becoming part of the geological record, frozen into the very structure of the Moon itself. Future explorers might find your remains embedded in a pressure ridge, a human fossil preserved in alien ice. But perhaps the most haunting aspect of dying on Europa would be knowing that just a few miles beneath your feet lies an ocean that might harbor life. As your consciousness faded in the radiation-soaked cold, you'd be dying on top of what could be the most biologically significant body of water in the solar system. The irony would be almost unbearable if you lived long enough to appreciate it. Your body would become part of Europa's surface ice, slowly sublimating away into the thin atmosphere over geological time. The water that once flowed through your veins would eventually make its way down through cracks in the ice, joining the subsurface ocean that you could never reach in life. In a sense, part of you would finally make it to that hidden sea, becoming one with the waters that might nurture alien life forms beyond our wildest imagination. Next, we journey to Ganymede, Jupiter's largest moon and the biggest satellite in our entire solar system. Ganymede is larger than Mercury, possesses its own magnetic field, and harbours yet another subsurface ocean beneath its icy crust. But dying on Ganymede would offer its own unique cocktail of environmental hazards that set it apart from its sister moons. The surface temperature on Ganymede averages around -290 degrees Fahrenheit, cold enough to freeze carbon dioxide solid. The atmosphere is incredibly thin, composed mainly of oxygen produced by the radiolysis of water ice, but at pressures so low that it might as well be vacuum for all the good it would do your lungs. What makes Ganymede particularly interesting as a place to die is its complex surface geology. The moon is divided into two distinct terrain types: ancient, heavily cratered dark regions, and younger, lighter areas covered with intricate groove systems that speak of massive geological upheaval. Depending on where you found yourself, your death would unfold against dramatically different backdrops. In the dark terrain, you die surrounded by impact craters that have remained virtually unchanged for billions of years. These ancient scars tell the story of the early solar system, where massive chunks of rock and ice regularly bombarded the moons of Jupiter. Your final resting place would be among geological features older than complex life on Earth, making you part of a landscape that predates most of the evolutionary history of your own species. In the grooved terrain, death would come amid evidence of Ganymede's more dynamic past. These strange parallel ridges and valleys, some stretching for hundreds of miles, were carved by processes we still don't fully understand. You'd be dying in a landscape that challenges our understanding of how icy worlds evolve, your body becoming part of a geological mystery that future scientists might ponder for centuries. Ganymede's magnetic field, while too weak to protect you from Jupiter's radiation, would create its own unique effects during your final moments. Charged particles from Jupiter would interact with this magnetic field, creating auroras that would dance across the sky as you died. Your last sight might be ethereal curtains of light, ghostly green and blue glows that would provide a hauntingly beautiful backdrop to your demise. The radiation environment on Ganymede, while less intense than on Io or Europa, would still be lethal. You'd receive a fatal dose in about a week, giving you time to fully appreciate the alien landscape around you before succumbing to radiation sickness. Your body would slowly shut down as your cells lost their ability to repair the damage caused by high-energy particles, a gradual failure of the biological machinery that keeps you alive. Our final stop in the Jovian system takes us to Callisto, the most distant of Jupiter's 4 large moons. Callisto is an ancient world, its surface saturated with impact craters that tell the story of 4.5 billion years of cosmic bombardment. It's the most heavily cratered object in the solar system, a museum of solar system violenced rock. Dying on call, preserved in ice Callisto, would be a relatively peaceful affair compared to the other Galilean moons. The radiation environment is much gentler, though still lethal over time. The surface temperature hovers around -300 degrees Fahrenheit, cold enough to kill you quickly, but not so extreme as to flash freeze you instantly. What makes Callisto unique as a place to die is its incredible age and stability. The surface you'd collapse upon has remained virtually unchanged for billions of years. The crater you might die in could have been formed when Earth was still a molten ball of rock, before the first oceans condensed, before the first life sparked into existence. Your body would join a landscape that has witnessed the entire history of the solar system. Every major impact event, every close encounter with other celestial bodies, every change in the sun's output over geological time has been recorded in Callisto's ancient surface. You'd become part of this cosmic archive, your atoms eventually scattered across a world that serves as the solar system's longest-running geological experiment. The view from Callisto would be spectacular in its own way. Jupiter would appear smaller than from the other Galilean moons, but still dominate the sky with its swirling atmospheric patterns. The other moons would be visible as bright points of light, each one a world in its own right, each one harboring its own unique ways of ending human life. As we prepare to leave the Jovian system and venture even further from the Sun, it's worth reflecting on what we've learned about dying in these strange worlds. Each moon offers its own signature method of termination, its own unique combination of environmental hazards that would challenge human physiology in ways our species never evolved to handle. But Jupiter's moons are just the beginning of our morbid tour. As we travel outward to Saturn, Uranus, and Neptune, we'll encounter worlds even more alien, environments even more hostile, and deaths so exotic they stretch the boundaries of what we can imagine. The ice geysers of Enceladus, the hydrocarbon lakes of Triton, the diamond rain of Neptune's moons all await us in the outer reaches of our solar system. Each world we visit will teach us something new about the fragility of human life and the incredible diversity of environments that exist in our cosmic neighborhood. And with each death we explore, we'll gain a deeper appreciation for the remarkable set of conditions that make life possible on our own pale blue dot, suspended in the cosmic dark. The outer solar system beckons us with promises of death so exotic, so utterly alien, that they would make the violent moons of Jupiter seem almost hospitable by comparison. As we journey beyond the asteroid belt and into the realm where sunlight becomes a distant memory, we encounter Saturn's magnificent court of satellites, each one a masterpiece of cosmic lethality. Saturn commands over 80 moons, but none captures the imagination quite like Triton, the second largest moon in our solar system, and the only satellite known to possess a thick atmosphere and stable liquid on its surface. But don't let these Earth-like qualities fool you into thinking Triton would be a comfortable place to meet your end. Triton's atmosphere is 4 times denser than Earth's, composed primarily of nitrogen, with a significant methane component that creates a thick orange haze obscuring the surface. The atmospheric pressure at ground level is about 50% greater than Earth's, meaning you could actually survive without a pressure suit. But surviving the pressure and surviving Triton are 2 entirely different propositions. The surface temperature on Triton hovers around -290 degrees Fahrenheit, cold enough to turn water into rock-hard ice and methane into flowing liquid. Yes, you read that correctly. On Triton, methane behaves the way water does on Earth, forming clouds, falling as rain, carving river channels, and collecting in vast lakes and seas. Imagine drowning in liquid methane. The very concept challenges our understanding of what drowning means. Methane is less dense than water, so your body would float more readily. But it's also far less viscous, offering little resistance to your movements. You'd sink slowly through the frigid liquid, your body temperature rapidly equalizing with the -290-degree methane around you. The cold would kill you long before you could actually drown. Your blood would begin to freeze within seconds, ice crystals forming in your circulatory system, like microscopic daggers cutting you apart from the inside. Your brain would shut down almost instantly as the neural pathways that define your consciousness literally crystallized into inert ice. But here's where Triton's death becomes truly surreal. The methane lakes on Triton are so cold and pure that your body wouldn't decompose in any recognizable way. Instead, you'd become a perfectly preserved corpse, floating in an alien sea. Your flesh turned into something resembling frozen meat, your bones transformed into structures harder than concrete. The lake itself would become your eternal tomb. Triton's methane cycle means that these bodies of liquid persist for thousands of years, slowly evaporating and reforming as the seasons change on this distant world. Your body could spend millennia floating in liquid methane, occasionally exposed as lake levels drop, then submerged again as methane rains replenish the seas. The atmosphere above would be equally hostile. While you could breathe the nitrogen component, the lack of oxygen would cause you to suffocate within minutes. The methane content would act like an anesthetic, potentially causing you to lose consciousness before the hypoxia became unbearable. Your final moments would be spent in a hazy, dreamlike state as your brain slowly starved for oxygen. But perhaps most unsettling would be the view. Titan's thick atmosphere creates a perpetual twilight, even during the day. The sun would be invisible, hidden behind layers of orange haze that filter out most of the light. You'd die in a world of perpetual sunset, where the horizon glows with an eerie amber light that never changes, never brightens, never offers the hope of a new dawn. Your body would eventually become part of Titan's complex organic chemistry. The moon's atmosphere is constantly creating complex hydrocarbon molecules through photochemical reactions. These organic compounds rain down onto the surface like cosmic snow, building up layers of material that could one day become the building blocks for life. In death, you'd join this process. Your carbon-based body would slowly break down and become incorporated into Titan's organic inventory. Your atoms potentially contributing to the formation of molecules that might, millions of years in the future, spark the first stirrings of life on this distant world. Moving inward from Titan, we encounter Enceladus, Saturn's ice-covered moon that has captured the attention of astrobiologists worldwide. Enceladus is small, only about 300 miles in diameter, but it harbors one of the most spectacular phenomena in the solar system: massive geysers of water ice erupting from its south polar region. These aren't gentle fountains of water. These are violent eruptions that shoot ice particles and water vapor hundreds of miles into space at supersonic velocities. The geysers are powered by tidal heating from Saturn's gravity, which keeps a subsurface ocean liquid beneath the moon's icy crust. Dying on Enceladus would depend entirely on where you found yourself on its surface. If you landed in the relatively quiet northern regions, your death would be similar to Europa, a combination of intense cold, vacuum conditions, and radiation exposure. The surface temperature averages around minus 330 degrees Fahrenheit, cold enough to freeze nitrogen solid. But if fate deposited you near the South Polar region, your death would be far more dramatic. The famous tiger stripe fractures that crisscross this region are essentially giant cracks in the ice, some of them actively venting material from the subsurface ocean. Standing near one of these fractures would be like standing next to a cosmic geyser that could erupt without warning. If you were caught in one of these eruptions, death would be instantaneous and spectacular. You'd be hit by a supersonic blast of ice particles and water vapor traveling at speeds of up to 1,500 miles per hour. The impact would pulverize your body instantly, turning you into a cloud of organic particles that would join the geyser plume shooting into space. Your atomized remains would become part of Saturn's E-ring, the gossamer ring of ice particles that Enceladus continuously feeds through its geysers. In a very real sense, you'd become part of one of the most beautiful structures in the solar system, your atoms scattered across thousands of miles of space in a glittering arc around Saturn. Some of your particles might even escape Saturn's gravity entirely, eventually making their way to other moons or even other planets. You'd become the first human to achieve natural interplanetary distribution, your atoms scattered across the solar system by the explosive power of an alien geyser. For those particles that remained in orbit around Saturn, the view would be incomparable. Saturn's rings would stretch across the sky in magnificent arcs of light and shadow, constantly changing as the planet's rotation creates new patterns of illumination. Your scattered atoms would witness sunrises and sunsets unlike anything possible from a planetary surface, as the rings create complex shadow patterns that dance across space. The subsurface ocean that powers Enceladus's geysers represents one of the most promising locations for finding life beyond Earth. As your atomized remains eventually settle back onto the Moon's surface, some of your particles might work their way down through cracks in the ice, eventually reaching that hidden sea. In death, you could become the first human to enter an alien ocean, your organic molecules potentially providing nutrients for whatever life forms might exist in those dark, warm waters. It's a death that would make you not just a casualty of space exploration, but potentially a contributor to astrobiology, your atoms becoming part of the very ecosystem scientists hope to study. Venturing to Saturn's largest moon after Titan, we find Iapetus, a world so strange, it seems like it was designed by a committee of alien architects who couldn't agree on a single design philosophy. Iapetus is a moon of stark contrasts, with one hemisphere as dark as charcoal and the other as bright as fresh snow. The temperature difference between these regions creates thermal stress that has literally reshaped the moon's surface. Dying on Iapetus would be a study in extremes. If you found yourself on the dark hemisphere, known as Cassini Regio, you'd experience surface temperatures around -230 degrees Fahrenheit. The dark material, possibly composed of organic compounds, would absorb what little sunlight reaches Saturn's distance from the Sun, creating a slightly less hostile environment than the bright regions, but land on the bright hemisphere, and you'd face temperatures approaching -280 degrees Fahrenheit. The bright ice reflects almost all incoming sunlight, creating a frozen wasteland that makes Antarctica look tropical. Your body would freeze solid within minutes, becoming a sculpture of human anatomy preserved in the cosmic cold. The most remarkable feature of Iapetus is its equatorial ridge, a chain of mountains that circles the moon's equator like a cosmic weld seam. These peaks rise up to 12 miles high, taller than Earth's mountains despite Iapetus's much smaller size and weaker gravity. If you found yourself dying on one of these peaks, you'd have a view that no human has ever experienced. From the top of Iapetus's equatorial ridge, you could see the curvature of the moon beneath you with startling clarity. Saturn would hang in the black sky like a jeweled ornament, its rings edge on from Iapetus's perspective, appearing as a thin line of light, bisecting the giant planet. The contrast between the dark and bright hemispheres would be visible as a stark boundary, cutting across the landscape below. Your death on Iapetus would be witnessed by one of the most geologically puzzling landscapes in the solar system. Scientists still don't fully understand how the equatorial ridge formed, or why the moon's hemispheres are so dramatically different. Your final resting place would be among mysteries that challenge our understanding of planetary formation and evolution. As we prepare to leave Saturn's system and venture even further from the Sun, we encounter worlds where the very concepts of warmth and light become abstract memories. The outer solar system holds moons where death takes on forms so alien that they stretch our language to its breaking point. Uranus, that tilted giant rolling on its side through space, commands a retinue of moons named after characters from Shakespeare and Alexander Pope. These worlds exist in a realm where the Sun appears as little more than a bright star, where temperatures plummet to levels that would freeze solid most of the gases we consider fundamental to existence. Miranda, the smallest of Uranus's major moons, presents a landscape that looks like it was shattered and reassembled by cosmic forces. The moon's surface is a patchwork of different terrains, suggesting that it was once broken apart by a massive impact and then gravitationally reassembled into its current form. Dying on Miranda would place you in a world that has literally experienced death and resurrection on a planetary scale. The surface features massive canyons and cliff faces that dwarf anything on Earth, including Verona Rupes, a cliff that drops for 12 miles into darkness. If you fell from this precipice, you'd have time to contemplate your situation for several minutes before impact, falling in Miranda's weak gravity like a feather through the thin, virtually non-existent atmosphere. The surface temperature on Miranda averages around -335 degrees Fahrenheit, cold enough to freeze methane solid and turn nitrogen into liquid. Your body would freeze so completely that it would become more brittle than glass, shattering if disturbed by even minor impacts from micrometeorites. But perhaps the most haunting aspect of dying on Miranda would be the silence. The moon is so far from the sun that solar wind effects are minimal, and its virtually non-existent atmosphere means no weather, no wind, no sound, except what you might generate yourself in your final moments. You die in a silence so complete, it would be like experiencing the absence of existence itself. Your body would remain on Miranda's surface for geological ages, slowly accumulating a coating of dust from micrometeorite impacts. Over millions of years, you'd become buried under layers of cosmic debris, eventually becoming part of the geological record of this strange, reassembled world. The view from Miranda would be dominated by Uranus itself, appearing as a featureless blue-green disk in the sky. The planet's bizarre tilted rotation means that its poles alternately face the sun during its 84-year orbit, creating seasons that last for decades. You might die during Miranda's decades-long winter, when Uranus's pole points away from the sun, or during its equally long summer, when the pole faces our distant star. As we venture into the outermost reaches of our solar system, we encounter Neptune's moons, worlds so distant that they exist in a realm where the sun provides less warmth than a full moon does on Earth. These are places where death takes on an almost abstract quality, where the normal processes of biology become impossible not just because of the cold, but because the very concept of warmth becomes meaningless. Triton, Neptune's largest moon, is a captured Kuiper belt object that orbits the planet backward, suggesting a violent capture event in the distant past. It's one of the coldest places in the solar system, with surface temperatures averaging -391 degrees Fahrenheit, just 68 degrees above absolute zero. At these temperatures, nitrogen becomes liquid and falls as snow. The surface is covered with frozen nitrogen, methane, and carbon monoxide, creating a landscape that would be unrecognizable to anyone familiar with Earth's geology. Dying on Triton would place you in an environment so alien that the very air you exhale would instantly crystallize and fall to the ground like glittering sand. But Triton harbors its own surprising activity. Despite the incredible cold, the moon has geysers that shoot dark material up to 5 miles above the surface. These aren't water geysers like those on Enceladus, but eruptions of nitrogen gas heated by the weak sunlight and carrying dark particles into the thin atmosphere. If you were unlucky enough to be caught in one of these nitrogen geysers, your death would be both instant and bizarre. The supersonic blast of nitrogen gas would freeze you solid while simultaneously launching your body into the thin atmosphere. You'd become a human projectile, frozen solid and traveling at hundreds of miles per hour through Triton's tenuous sky. Your frozen body would eventually fall back to the surface like a macabre meteorite, impacting the nitrogen snows with enough force to create your own small crater. This crater would become a permanent memorial to human exploration, preserved in the frozen nitrogen for millions of years until geological processes eventually erased it. The view from Triton would be unlike anything else in the solar system. Neptune would appear as a brilliant blue star in the sky, far brighter than any other object, but still providing less light than a dim bulb. The other moons of Neptune would be invisible to the naked eye, appearing as faint points of light, indistinguishable from distant stars. Your death on Triton would occur in one of the most isolated places in the known universe, a world so far from the sun that it exists in perpetual twilight, where the boundary between day and night loses all meaning. You'd become part of a landscape that has remained essentially unchanged for billions of years. Your atoms eventually incorporated into the geological processes of a world that has witnessed the entire history of the outer solar system. As we continue our journey through Neptune's system and beyond, we'll encounter worlds even more remote, moons of the dwarf planets that exist in the twilight zone between our solar system and interstellar space. These are places where death becomes not just a biological process, but a fundamental encounter with the absolute cold and darkness of the cosmic void. The dwarf planets that lurk in the outer darkness of our solar system command their own retinue of moons, worlds so remote that they exist in a realm where the sun becomes just another star in the cosmic tapestry. These are places where the very notion of solar influence becomes a philosophical concept rather than a physical reality, where dying would connect you to the fundamental coldness of the universe itself. Pluto's largest moon, Charon, represents a unique case in our solar system. The two bodies are so similar in size that they form what astronomers call a binary system, locked in a gravitational dance where they show the same face to each other for eternity. Dying on Charon would place you in a world where Pluto hangs motionless in the sky, a rust-colored disk that never moves, never sets, never rises. The surface temperature on Charon averages around -380 degrees Fahrenheit, approaching the theoretical limits of cold in our solar system. At these temperatures, even the hardy gases that remain active on other outer moons become solid. Your final breath would contain water vapor that would instantly transform into ice crystals so fine they would resemble microscopic diamonds, each one a perfect geometric structure created by the absolute cold. Your body would undergo transformations that would be impossible anywhere else we've visited. The extreme cold would cause your tissues to contract so dramatically that your bones would become more brittle than spun glass. Any movement, even the involuntary spasms of dying, could cause your skeleton to fracture into countless pieces, creating a grotesque jigsaw puzzle of human anatomy scattered across the alien landscape. But here's what makes dying on Charon particularly haunting. The moon's surface is covered with a reddish material that scientists believe comes from Pluto itself, organic compounds called tholins that are created when cosmic radiation interacts with methane and nitrogen. This gives Charon a rust-colored appearance that would provide a warm visual contrast to the absolute cold that would be killing you. Your death would unfold against a backdrop of crystalline water ice canyons that stretch for hundreds of miles across Charon's surface. These massive rifts suggest that the moon once had a subsurface ocean that froze and expanded, cracking the surface like an eggshell. You'd be dying on a world that has already experienced its own form of death, the freezing of its internal ocean billions of years ago. The lighting conditions on Charon would create an otherworldly atmosphere for your demise. The sun, appearing as nothing more than a bright star, would cast sharp, high-contrast shadows across the landscape. There would be no atmospheric scattering to soften the light, no blue sky to provide context, just the harsh illumination of unfiltered starlight, creating a chiaroscuro landscape of brilliant whites and absolute blacks. Your body would become part of Charon's slow geological evolution. The moon experiences micrometeorite bombardment that gradually pulverizes surface materials over millions of years. Eventually, your frozen remains would be ground into dust particles that would migrate across the surface through processes we're only beginning to understand. You'd become part of Charon's regolith, contributing your atoms to the slow mixing process that shapes the surface of this distant world. Pluto's other moons, Styx, Nix, Kerberos, and Hydra, are even smaller and more irregular, basically chunks of ice and rock tumbling through the outer darkness. Dying on any of these tiny worlds would be like dying on a cosmic iceberg, surrounded by a landscape so alien that it would challenge your ability to process visual information even in your final moments. These small moons have such weak gravity that your death throes could literally launch you into space, turning your dying body into its own miniature spacecraft. You might spend your final moments of consciousness floating away from the moon's surface, watching it recede below you as you drift into the interplanetary void. Death would come not from impact or environmental exposure, but from the gradual expansion of space between you and any solid surface, a uniquely cosmic form of isolation. The irregular shapes of these moons would create landscapes unlike anything in the inner solar system. Imagine dying on a world where the horizon curves upward in some directions and downward in others, where the concept of up and down becomes meaningless because the gravitational field is so weak and irregular. Your final visual experience would be of a reality that defies every intuitive understanding of how worlds should look. But even these remote outposts of our solar system pale in comparison to the truly exotic moons that orbit some of the most distant objects we've discovered. As we venture beyond Neptune's orbit into the Kuiper belt and beyond, we encounter worlds so far from the Sun that they exist in a perpetual deep freeze that has persisted since the formation of the solar system. Eris, one of the dwarf planets beyond Pluto, has a moon called Dysnomia that represents perhaps the most extreme environment for death we've yet encountered. The surface temperature here drops to -405 degrees Fahrenheit, just 55 degrees above absolute zero. At these temperatures, the normal rules of chemistry begin to break down. Molecules move so slowly that chemical reactions essentially stop, creating a world where even the processes of decay become impossible. Dying on Dysnomia would be like dying at the edge of existence itself. Your body would freeze so completely that it would become a perfect crystal structure, every cell transformed into a geometric arrangement of frozen biomolecules. You wouldn't decompose, you wouldn't change, you would simply become a permanent sculpture of human anatomy, preserved in the cosmic cold for potentially billions of years. The radiation environment in the outer solar system creates its own unique hazards. While the intensity is much lower than in the inner system, the composition is different. You'd be bombarded by cosmic rays that have traveled for millions of years through interstellar space, carrying with them the nuclear signatures of distant supernovas and stellar explosions. Your death would be witnessed by radiation that began its journey when entirely different stars dominated the galaxy. The Kuiper belt objects and their moons represent a museum of solar system formation, worlds that have remained essentially unchanged for 4.5 billion years. Would connect you to the dying on one of these ancient surfaces' primordial materials from which our entire solar system formed. The ice beneath your feet would contain water that predates Earth itself, organic molecules that represent the chemical building blocks from which life eventually emerged. Your atoms would join this ancient inventory, becoming part of a chemical archive that preserves the conditions of the early solar system. Future explorers who eventually reach these distant worlds might find your remains not as evidence of human exploration, but as a geological sample that tells the story of how complex organic chemistry can emerge even in the most hostile environments. The view from these distant moons would provide a perspective on our solar system that no human has ever experienced. The sun would appear as just another star, indistinguishable from the thousands of other points of light scattered across the sky. Earth would be completely invisible, lost in the glare of our distant star. You'd be dying with a view that encompasses the entire solar system as a single point of light, surrounded by the infinite darkness of interstellar space. But perhaps the most profound aspect of dying on these remote worlds would be the complete severance from everything that has defined human existence. No weather, no seasons, no day-night cycle in any meaningful sense. Just the eternal cosmic night, broken only by the slow rotation of unfamiliar constellations as your final resting place tumbles through space on its ancient orbit. The silence would be absolute in ways that are difficult to comprehend. No atmosphere means no sound transmission, but more than that, these worlds exist so far from any significant gravitational disturbances that even the subtle flexing and creaking that affects inner solar system bodies becomes negligible. You die in a silence so complete that it would represent the absence of mechanical vibration itself. Your legacy on these distant worlds would be measured in geological time. The surface processes that might eventually bury or disperse your remains operate so slowly that your body could remain exposed and recognizable for millions of years. You'd become a landmark on an alien world, a reference point that future explorers might use to navigate the exotic terrain of humanity's most distant outpost. As we consider the moons of the most distant objects in our solar system, we encounter worlds where the very concept of environment becomes abstract. These are places where the normal categories we use to describe planetary conditions, temperature, pressure, atmospheric composition, become almost meaningless because they represent such extreme departures from anything life could possibly adapt to. The recently discovered moons of objects in the scattered disk and Oort cloud exist in conditions so severe that they challenge our understanding of what it means for matter to exist in organized form. These worlds experience temperatures so low that even helium would freeze solid, creating landscapes composed of materials that exist nowhere else in the solar system. Dying on one of these ultra-distant moons would be like experiencing the heat death of the universe in miniature. Your body would cool to match the ambient temperature so quickly that the process of dying would be interrupted by the complete cessation of all molecular motion. You wouldn't die in the biological sense, so much as you would transition directly from life to a state that resembles the theoretical end state of the cosmos itself. The timescales involved in these distant realms stretch human comprehension to its limits. Your body, preserved in the absolute cold, could remain essentially unchanged for periods longer than the current age of the universe. You would become part of a world that exists almost outside of time, where geological processes operate so slowly that the surface you died on might remain virtually identical for longer than complex life has existed on Earth. These ultimate frontiers of our solar system represent more than just exotic places to die. They are laboratories for understanding the fundamental limits of existence, places where the normal rules of chemistry, physics, and biology are pushed to their breaking points. Your death on one of these worlds would make you part of an experiment in extremes, a test case for how matter behaves under conditions that approach the theoretical limits of physical possibility. The irony is profound. These worlds that would kill you most efficiently are also the ones that would preserve you most perfectly. In the absolute cold and perfect vacuum of the outer solar system, your body would become a time capsule, a snapshot of human biology, preserved with a fidelity that no earthly mummification process could achieve. As our morbid tour of the solar system's moons continues to push us toward ever more extreme environments, we begin to understand something fundamental about the nature of existence itself. Life, consciousness, the complex chemistry that makes us possible. All of these emerge from an incredibly narrow range of conditions that exist almost nowhere else in our cosmic neighborhood. Every moon we've visited tells the same story from a different angle. The universe is not hostile to life so much as it is indifferent to it. These worlds don't actively seek to kill us. They simply exist in states that are incompatible with the delicate chemical processes that define biological existence. They are beautiful, ancient, complex, and utterly alien to everything that makes life possible. Yet in their very alienness, they teach us something precious about our own world. Earth is not just a planet among planets. It is an almost impossibly rare exception to the cosmic rule. The gentle embrace of our atmosphere, the protective shield of our magnetic field, the perfect distance from our star that keeps water liquid, all of these represent a convergence of conditions so unlikely that they border on the miraculous. Our journey through the deadly moons of the solar system reveals Earth not as a prison that confines us, but as a sanctuary that protects us from a universe filled with wonders that would kill us instantly. Every breath you take, every heartbeat that pushes blood through your veins, every thought that crosses your consciousness, all of these are acts of defiance against a cosmos that operates according to rules that make life almost impossible. The moons we've explored represent just the beginning of our cosmic neighborhood. Beyond our solar system lie worlds even more exotic, environments even more hostile, and deaths so alien that they would make our local moons seem positively welcoming by comparison. But that is a journey for another time, a descent into cosmic horror that would require us to abandon even our most basic assumptions about what it means to exist in this strange and wonderful universe. For now, as we contemplate the deadly beauty of our solar system's satellite worlds, we can rest in the knowledge that we are perfectly positioned to appreciate their lethal magnificence from the safety of our pale blue dot. We can explore these worlds through the power of imagination and scientific observation, experiencing their exotic forms of death without actually dying, understanding their alien nature without having to surrender our human one. The moons of our solar system stand as monuments to the creativity of cosmic forces, each one a unique solution to the problem of how matter organizes itself in the cold darkness of space. They are beautiful, terrible, ancient, and strange. They are laboratories where the universe experiments with the limits of physical possibility. And they are places where human death would take on forms so exotic that they expand our understanding of what it means to be alive in the first place. In this grand theatre of cosmic lethality, we've barely scratched the surface of what the outer solar system has to offer. As we venture even further from the sun's dying light, we encounter realms where the very atoms that compose your body would behave in ways that challenge our understanding of matter itself. Consider the moons of Makemake, one of the most distant dwarf planets in our solar system. Here, in a realm where the sun appears as nothing more than an unusually bright pinprick against the stellar background, we find worlds where death transcends the merely physical and becomes something almost metaphysical in its completeness. The surface temperature on these ultra-distant bodies approaches minus 415 degrees Fahrenheit, a cold so profound that it begins to affect the quantum behavior of atoms themselves. At these temperatures, the random thermal motion that keeps atoms jiggling in their molecular arrangements slows to an almost complete stop. Your body wouldn't just freeze, it would enter a state that physicists call quantum crystallization, where the very structure of matter becomes locked into perfect geometric patterns. Imagine dying in a place where your final breath creates ice crystals so perfect, so geometrically precise, that they resemble microscopic works of art. Each water molecule from your lungs would arrange itself in crystalline structures, more flawless than any diamond, creating a constellation of frozen beauty around your collapsing form. These crystals would be so stable in the absolute cold that they could persist unchanged for billions of years, each one a tiny monument to your last moment of biological function. But the cold would only be the beginning of your transformation on these distant worlds. The radiation environment in the outer solar system is dominated not by solar particles, but by cosmic rays from deep space, high-energy particles that have traveled for millions of years across the galaxy. These cosmic rays carry within them the nuclear signatures of stellar explosions that occurred when the galaxy was young, when entirely different regions of space were forming the heavy elements that would eventually become planets and moons and you. As you died on one of these remote satellites, you'd be bombarded by radiation that began its journey before our solar system even existed. Particles accelerated by supernovas that exploded when the Milky Way was still forming its spiral structure would pass through your body, each one carrying information about cosmic events that predate everything familiar in our local stellar neighborhood. The gravitational environment on these tiny, distant moons creates its own unique choreography of death. With surface gravity often less than 1,000th of Earth's, your dying body could easily achieve escape velocity through the simple act of convulsing. You might find yourself launched into space by your own death throes, beginning an independent orbit around the dwarf planet as a human satellite. This macabre scenario would transform your corpse into the solar system's most distant human artifact. You'd become a miniature moon yourself, following an elliptical path that could persist for millions of years. Future space archaeologists might discover your orbit long before they find the surface from which you were launched, puzzling over the trajectory of what appears to be a perfectly preserved human body sailing through the void. The timescales involved in these outer reaches stretch beyond human comprehension. Your body, launched into its own orbit, could complete thousands of revolutions around these distant dwarf planets before gravitational perturbations eventually cause you to crash back to the surface. During this time, you'd witness thousands of the slow, stately rotations of these ancient worlds, each one taking you past landscapes that have remained unchanged since the solar system's formation. The surface features of these ultra-distant moons tell stories written in the language of pristine preservation. Impact craters from the solar system's violent youth remain as fresh as the day they were formed, unaltered by weather, unmodified by geological activity, unmarked by the passage of time. You'd be dying among artifacts from the cosmic dawn, surrounded by geological features that were ancient when Earth was still a molten ball of rock. Your landing site, whether achieved through direct impact or eventual orbital decay, would become part of this primordial landscape. The crater formed by your impact would join the collection of scars that record the history of cosmic bombardment, though yours would be unique in containing organic compounds that speak of life's brief flowering in a distant part of the solar system. The chemical composition of these outer moons presents its own exotic challenges to human survival. Many contain significant amounts of methane and nitrogen ices, materials that would sublimate directly into gas if disturbed by the heat of your dying body. You could find yourself sinking into a surface that literally evaporates beneath you, creating a cloud of vapor that would instantly refreeze in the cosmic cold. This process would create a unique form of geological immortality. Your body heat, the last expression of your biological processes, would reshape the immediate landscape around your death site. The sublimated and refrozen materials would create a kind of human-influenced stratigraphy, layers of ice that record the thermal signature of your dying moments. Future geologists studying these formations might be able to read the story of your death in the crystal structure of the refrozen volatiles. The magnetic environment of these distant worlds adds another layer of complexity to the dying process. Far from the sun's magnetic field and possessing no significant magnetic fields of their own, these moons exist in the unfiltered cosmic magnetic environment. The interstellar magnetic field, weak but persistent, would interact with any metallic components in your body in ways that have never been observed. Your blood, rich in iron, might align itself with these cosmic magnetic field lines in your final moments, creating patterns in your circulatory system that reflect the magnetic geography of interstellar space. It's a death that would literally orient your body according to the magnetic structure of the galaxy itself, making you a biological compass pointing toward magnetic north in the cosmic reference frame. The atmospheric conditions on these worlds, where they exist at all, are so tenuous that they challenge our definition of what constitutes an atmosphere. The few gas molecules present are often escape products from sublimating surface ices, creating wisps of vapor so thin that they're measured in individual molecules per cubic centimeter, rather than any meaningful pressure. Breathing such an atmosphere would be like trying to extract oxygen from the vacuum of space itself. Your lungs would expand uselessly, drawing in volumes of near-nothingness that contain fewer gas molecules than exist in the most perfect vacuum chambers on Earth. The act of respiration would become a cosmic joke, your respiratory system going through the motions of breathing while accomplishing nothing except the expulsion of your own water vapor into the void. These expelled water molecules would join the thin atmospheric inventory of the Moon, becoming part of its hydrological cycle on timescales measured in geological epochs. Your final breaths would contribute to weather patterns so slow that a single atmospheric circulation might take thousands of years to complete. You'd become part of meteorological processes that operate on timescales that dwarf human civilization. The lighting conditions on these ultra-distant worlds create visual experiences that no human has ever witnessed. The sun, reduced to stellar dimensions, casts shadows so sharp and high contrast that they appear almost two-dimensional. Without atmospheric scattering to soften the illumination, the landscape exists in a state of absolute chiaroscuro, where surfaces are either brilliantly lit or completely black. Your dying eyes would struggle to process this alien lighting environment. The human visual system evolved under Earth's atmosphere, which scatters blue light and creates the gradual transitions between light and shadow that we consider normal. On these distant worlds, the absence of atmospheric scattering would create visual conditions so stark that your brain might struggle to interpret the scene, even as consciousness faded. The thermal environment presents challenges that go beyond simple cold. At temperatures approaching absolute zero, materials behave in ways that seem to violate common sense. Your clothing, if you wore any, might become superconducting, allowing electrical currents to flow through it without resistance. Any metallic objects on your person could exhibit quantum properties normally confined to laboratory conditions. Your body itself would become a physics experiment as it cooled to match the ambient temperature. The water in your tissues would freeze into exotic, crystalline phases that don't exist under normal conditions, creating internal structures that are more akin to semiconductor materials than biological tissue. You'd be transformed into a hybrid of organic chemistry and quantum physics, a human body that exhibits properties normally associated with advanced materials science. The preservation potential in these environments approaches the theoretical limits of what's possible in nature. Your body would cool so quickly and completely that even the bacteria normally responsible for decomposition would be frozen solid before they could begin their work. You'd become more perfectly preserved than any mummy, any fossil, any biological specimen ever discovered on Earth. This preservation would be so complete that future explorers, arriving perhaps millions of years after your death, might find your body in a state that appears almost alive. Your cellular structure would be intact, your DNA readable, your proteins still folded in their functional configurations. You'd represent a time capsule of human biology, preserved with a fidelity that no earthly process could achieve. The geological context of your death would place you among the most ancient surfaces in the solar system. These outer moons have experienced virtually no geological activity since their formation, meaning that the ground you died on could be composed of materials that predate the existence of complex life on Earth. Your organic molecules would join a chemical inventory that has remained essentially unchanged for billions of years. This juxtaposition of the contemporary and the primordial would create a unique archaeological situation. Your remains would represent the most recent addition to landscapes that are otherwise museums of solar system formation. Future xenoarchaeologists studying these sites might find your body as the only evidence of recent activity on worlds that are otherwise perfect time capsules from the cosmic dawn. The orbital mechanics of these distant worlds create their own contributions to the death experience. Many of these moons follow highly elliptical orbits that carry them through regions of space with dramatically different radiation environments. Your death might occur during the moon's closest approach to its parent dwarf planet, when tidal forces create the only geological activity these worlds ever experience. The scale of isolation involved in these outer system deaths challenges human psychological frameworks for understanding loneliness. You'd be dying on worlds where the nearest other solid surface might be millions of miles away, where the concept of nearby loses all meaning. The isolation would be so complete that light from the nearest neighboring moon might take hours to reach you, meaning that even visual contact with other worlds would involve significant time delays. This cosmic loneliness would be compounded by the temporal isolation of these environments. The slow orbital periods and rotation rates of outer system objects mean that day-night cycles, where they exist at all, unfold over periods that dwarf human attention spans. You might die during a day that lasts for weeks or months, experiencing a kind of temporal displacement that separates you not just from other places, but from other rates of time itself. The magnetic field interactions in these regions create phenomena that exist nowhere else in our solar system. The boundary between our sun's magnetic influence and the interstellar magnetic field passes through these distant realms, creating regions where magnetic field lines from our star interact with magnetic structures that extend across light years of space. Your death might occur in a location where the magnetic environment literally connects you to nearby star systems. The magnetic field lines passing through your body could extend to other stellar magnetic fields, creating a physical connection between your dying moments and the magnetic environments of alien suns. It's a death that would integrate you into the galactic magnetic infrastructure, making you part of magnetic structures that span interstellar distances. The chemical evolution of these outer worlds provides the final context for understanding death in these extreme environments. The surfaces are composed largely of materials that have undergone no chemical evolution since the solar system's formation. The ices, organics, and rocky materials represent pristine samples of the chemical inventory from which planets formed. Your body, with its complex organic chemistry forged by billions of years of biological evolution, would represent the most chemically sophisticated material ever to reach these primitive surfaces. The contrast would be profound. The most advanced chemistry that life has achieved, meeting the most primitive chemistry that the solar system preserves. Your death would bring together the endpoints of chemical evolution, the primordial and the refined, in a meeting that spans the entire history of our cosmic neighborhood. As we contemplate these ultimate frontiers of death in our solar system, we begin to understand that we're exploring more than just exotic ways to die. We're examining the fundamental boundaries of existence itself, the places where the normal rules that govern life and death break down completely. These distant moons represent laboratories where the universe experiments with the limits of physical possibility, where matter and energy behave according to principles that stretch our understanding to its breaking point. The deaths we've explored on these remote worlds aren't just biological failures, they're transitions into states of existence that have no earthly equivalent. You wouldn't simply die on these worlds, you'd become something else entirely: a quantum crystal, a magnetic compass, a time capsule, a satellite, a geological feature. The boundaries between life and death, between biology and physics, between the organic and the inorganic, would blur in ways that challenge our most basic categories of understanding. Each moon in this distant realm offers its own unique transformation, its own signature method of converting human biology into something that transcends normal biological categories. You'd become part of processes that operate on timescales and spatial scales that dwarf human experience, integrated into cosmic systems that connect you to the fundamental structures of space and time themselves. The irony is beautiful and terrible. The places that would kill you most completely are also the places that would preserve you most perfectly, that would integrate you most thoroughly into the cosmic story, that would make you part of phenomena that span from the quantum scale to the galactic scale. These deaths wouldn't end your story, they'd transform it into something larger than human, something that participates in the deep structures that govern reality itself. Our journey through the deadly moons of the outer solar system reveals death not as an ending, but as a transformation into states of existence that we're only beginning to understand. In these remote, ancient, perfect worlds, the act of dying becomes an act of cosmic integration, a way of joining the fundamental processes that have been shaping matter and energy since the universe began. As we venture beyond even these distant realms, we encounter the forgotten moons of objects so remote they barely qualify as members of our solar system. Sedna, that mysterious wanderer, whose orbit carries it to distances where our sun becomes indistinguishable from background stars, commands at least one small satellite that exists in conditions so extreme they redefine what we mean by cosmic isolation. Here, in the twilight zone between our solar system and interstellar space, we find worlds where death becomes something approaching a philosophical concept rather than a biological process. The surface temperature on Sedna's moon hovers around -420 degrees Fahrenheit, just 40 degrees above absolute zero. At these temperatures, the normal rules of chemistry don't just break down, they become irrelevant. Your body would undergo a transformation so complete that the word death seems inadequate to describe it. As your tissues cooled to match the ambient temperature, the molecular motion that defines life would slow to an almost complete stop. You wouldn't die so much as you would transition into a state that resembles the theoretical heat death of the universe itself, becoming a perfect example of what physicists call maximum entropy. The water in your cells would freeze into crystalline structures so exotic they don't exist anywhere on Earth. These aren't the familiar hexagonal ice crystals we know from snowflakes, but bizarre polymorphs of ice that form only under conditions of extreme cold and pressure. Your body would become a museum of exotic crystal phases, each organ transformed into a different variety of impossible ice. But the truly unsettling aspect of dying on Sedna's moon would be the realization that you're experiencing conditions that represent the future state of the entire universe. Cosmologists predict that in trillions of years, when all the stars have burned out and all the black holes have evaporated, the universe will exist in a state very much like what you'd experience on this distant world. You'd be dying in a preview of cosmic death itself. The orbital period of Sedna carries it through a journey that takes over 11,000 years to complete. Your death would occur on a world whose seasons last longer than human civilization has existed. The astronomical context of your demise would dwarf every human story, every historical epoch, every cultural achievement our species has ever produced. Your frozen body would witness the passage of time on scales that make geological processes seem rapid. Entire ice ages on Earth would pass, while your crystallized remains completed a single orbit around this distant dwarf planet. You'd become part of a temporal framework so vast that it transforms the very meaning of permanence. The gravitational environment presents its own unique challenges to the dying process. Sedna's moon exists in a region where the gravitational influence of our sun becomes negligible compared to the tidal forces exerted by the galaxy itself. You'd be dying in a place where galactic mechanics dominate over solar system dynamics, where your body would be subject to forces that operate on scales measured in light years. These galactic tidal forces would be imperceptible to your dying nervous system, but they would subtly influence the orientation of your crystallizing body. Over the millions of years required for your remains to complete their slow orbital dance, these forces would gradually align your frozen form with the gravitational gradients that shape our galaxy's structure. The radiation environment in these outer reaches consists almost entirely of cosmic rays from deep space, particles that have traveled for millions of years across the galaxy before encountering your body. Some of these particles began their journey when our solar system was in an entirely different part of the galaxy, when different constellations dominated Earth's sky, when the cosmic environment was subtly but significantly different from what we observe today. As these ancient photons and particles pass through your crystallizing tissues, they carry with them information about stellar explosions that occurred before complex life existed on Earth. Your death would be illuminated by light that began its journey when the galaxy was younger, when different regions of space were undergoing star formation, when the cosmic chemical composition was measurably different from today's universe. The magnetic field environment at these distances exists at the boundary between our sun's magnetic influence and the interstellar magnetic field. Your body would become part of the heliopause region, where solar wind meets interstellar medium in a complex dance of charged particles and magnetic field lines that extends for billions of miles. The metallic components in your body, primarily the iron in your blood, would interact with these boundary magnetic fields in ways that have never been observed. Your circulatory system might become a biological magnetometer, recording the subtle variations in magnetic field strength that occur as your death site moves through different regions of the heliosphere boundary. These magnetic interactions would persist long after your biological death, creating a kind of electromagnetic fossil that records the magnetic history of the outer solar system. Future magnetic archaeologists might be able to reconstruct the evolution of our Sun's magnetic field by studying the magnetic alignment of iron particles in your preserved tissues. The chemical environment presents challenges that go beyond anything we've encountered on closer worlds. The surface materials on Sedna's moon consist largely of primordial ices that have remained unchanged since the solar system's formation. These aren't just frozen water, but exotic combinations of methane, nitrogen, carbon monoxide, and other volatiles that exist in proportions that reflect the original composition of the solar nebula. Your body would represent the first introduction of complex organic chemistry to these pristine surfaces. The amino acids, proteins, and DNA that compose your tissues would create chemical gradients in the surrounding ice that could persist for geological ages. You'd become the center of a slowly expanding zone of chemical complexity, introducing biological molecules to an environment that has known only the simplest chemical reactions for billions of years. The sublimation processes that occur, even at these extreme temperatures, would gradually distribute your organic molecules across vast areas of the moon's surface. Over millions of years, traces of your DNA could be spread across thousands of square miles, creating a molecular signature of human exploration that would be detectable to sufficiently sensitive instruments long after your body had been reduced to component atoms. The atmospheric conditions, where they exist at all, consist of individual molecules escaping from sublimating surface ices. The atmosphere might contain fewer than a dozen molecules per cubic meter, making it more tenuous than the best vacuum achievable in Earth laboratories. Breathing such an atmosphere would be like trying to extract oxygen from the space between galaxies. Your respiratory system would go through the futile motions of breathing while accomplishing nothing except the gradual loss of your own water vapor to the cosmic void. Each exhalation would contribute a few more molecules to the moon's gossamer-thin atmosphere, where they might persist for thousands of years before eventually escaping to interstellar space. These escape molecules from your lungs would eventually join the interstellar medium, becoming part of the vast clouds of gas and dust that exist between stars. Your final breaths would literally become part of interstellar space, contributing to the material from which future star systems might form. It's a form of cosmic recycling that operates on timescales measured in millions of years. The visual environment would challenge your dying brain's ability to process sensory information. The sun would appear as nothing more than a bright star, indistinguishable from dozens of other stars visible in the sky. Without any reference point to establish scale or distance, your visual cortex might struggle to interpret the alien landscape around you. The absence of atmospheric scattering would create lighting conditions unlike anything in human experience. Shadows would be perfectly black, illuminated surfaces perfectly bright, with no gradual transition between light and dark. Your dying eyes would witness a world that exists in a state of absolute contrast, where the normal visual cues that help us navigate three-dimensional space simply don't exist. The geological context of your death would place you among the most primitive materials in the solar system. The surface beneath your collapsing body would be composed of substances that predate the formation of planets, materials that represent direct samples of the conditions that existed in the early solar nebula. You'd be dying on a world that serves as a museum of cosmic formation processes. Your impact with this ancient surface would create the first significant geological event this world has experienced in billions of years. The heat generated by your body's collision with the ice would create a brief zone of chemical activity, melting and refreezing materials that have remained solid since before Earth existed. This impact site would become a unique geological formation, a human-influenced crater that records the thermal and chemical signature of your death. The refrozen materials around your body would contain isotopic ratios and chemical compositions that tell the story of your biological processes, creating a geological record of human physiology preserved in alien ice. The preservation potential in this environment approaches the theoretical maximum possible in nature. Your body would cool so rapidly and thoroughly that even quantum mechanical processes would slow to an almost complete stop. You'd achieve a state of preservation that's more perfect than any natural process has ever produced, becoming a biological specimen that could remain unchanged for longer than the current age of the universe. Future explorers discovering your remains might find your body in a state of preservation so perfect that your cellular structure remains intact at the molecular level. Your DNA would be readable, your proteins still folded in their functional configurations, your neural pathways still traceable through the crystallized structure of your brain tissue. The temporal context of your death would integrate you into processes that operate on cosmic timescales. Your orbital journey around this distant world would unfold over periods measured in millions of years, during which entire epochs of Earth's geological history would pass. You'd become part of astronomical phenomena that dwarf every human conception of permanence. The cosmic significance of dying in these remote reaches extends beyond the merely physical. You'd become part of the boundary region between our solar system and interstellar space, integrated into processes that connect our local stellar environment to the broader galactic community. Your death would make you a participant in phenomena that operate on scales from the quantum to the galactic. The isolation involved in these ultimate deaths challenges every human framework for understanding solitude. You'd be dying in locations where the nearest other solid surface might be light years away, where the concept of neighboring objects becomes meaningless in any human sense. The loneliness would be so complete that it approaches the theoretical limits of cosmic isolation. This extreme isolation would be compounded by the temporal displacement of these environments. The slow orbital and rotational periods mean that processes we consider fundamental to existence, like day-night cycles, unfold over timescales that exceed human comprehension. You'd be dying in a temporal framework that operates according to astronomical rather than biological rhythms. The magnetic connections at these distances would integrate you into structures that span interstellar space. The magnetic field lines passing through your body might extend to other star systems, creating physical connections between your death site and the magnetic environments of alien suns. You'd become part of magnetic structures that help organize matter and energy across vast regions of the galaxy. The chemical legacy of your death would persist long after your body had been reduced to component atoms. The complex organic molecules that compose human biology would represent the most sophisticated chemistry ever introduced to these primitive environments. Your biochemical signature would create zones of enhanced chemical complexity that could influence the evolution of these worlds for geological ages. The quantum mechanical effects that dominate at these extreme temperatures would transform your body into something that exists at the boundary between classical and quantum physics. Your tissues would exhibit properties normally associated with laboratory experiments in quantum mechanics, becoming a biological demonstration of quantum effects scaled up to macroscopic dimensions. As we contemplate these ultimate expressions of cosmic death, we begin to understand that we're exploring more than exotic ways for human life to end. We're examining the fundamental boundaries of existence itself, the places where normal categories of understanding break down completely. These deaths wouldn't just end your biological story, they'd transform it into something that participates in the deepest structures of physical reality. The moons of the most distant objects in our solar system represent the ultimate testing ground for human mortality. places where death becomes indistinguishable from transformation into cosmic phenomena. Here, the act of dying transcends biology and becomes a form of integration into the fundamental processes that govern space, time, matter, and energy across the universe. In these remote, ancient, perfect worlds, death reveals itself not as an ending, but as a transition into states of existence that operate according to principles we're only beginning to comprehend. You wouldn't simply cease to exist on these distant moons. You'd become something entirely new, something that bridges the gap between the biological and the cosmic, between the temporary and the eternal. Our cosmic tour of death has taken us to the very edges of what we can call our solar system. But there's one more category of worlds that demands our attention. The rogue moons, those wayward satellites that have been ejected from their parent systems and now wander the interstellar void as orphaned worlds, carrying with them the ultimate expression of cosmic loneliness. These nomadic bodies drift through the darkness between stars, unbound by any gravitational allegiance, following trajectories that will carry them through the galaxy for billions of years. They are the cosmic equivalent of ghost ships, sailing through an ocean of vacuum with no destination, no purpose, no connection to anything except the slow, inexorable pull of galactic rotation. Dying on a rogue moon would place you in the most isolated environment possible within our local stellar neighborhood. There would be no parent planet hanging in the sky, no other moons visible as points of reference, no sun to provide even the faintest warmth or light. Just you, the alien landscape, and the infinite star field that surrounds you in every direction. The temperature on these wandering worlds plunges to depths that make our previous encounters with cold seem almost tropical by comparison. We're talking about temperatures that approach minus 430 degrees Fahrenheit, just a few degrees above absolute zero. At these temperatures, even helium would freeze solid, creating surface compositions unlike anything we've encountered in our survey of solar system moons. Your body would undergo transformations that push the boundaries of what we understand about matter itself. As you cooled to match the ambient temperature, the quantum mechanical effects that normally operate only at the atomic level would begin to manifest in your macroscopic tissues. Your frozen flesh would exhibit properties that blur the line between biology and exotic physics. The water in your cells wouldn't just freeze, it would transition through multiple phase changes as the temperature dropped, forming crystalline structures that exist nowhere in nature except under these extreme conditions. Each phase transition would reshape your cellular architecture, creating internal geometries that would be more familiar to a material scientist than a biologist. Your nervous system, that intricate network of electrical signals that defines your consciousness, would undergo these temperatures. The organic, its own bizarre transformation. At superconductors in your neural tissue would begin to exhibit quantum coherence effects, potentially preserving the electrical patterns of your final thoughts in crystalline matrices that could persist for cosmic ages. The preservation would be so complete, so perfect, that your brain structure might retain not just its physical architecture, but actual information patterns. Future xenoarchaeologists with sufficiently advanced technology might be able to extract memories, thoughts, even fragments of consciousness from your quantum crystallized neural tissue. But perhaps the most unsettling aspect of dying on a rogue moon would be the knowledge that your death site is itself a cosmic wanderer, destined to drift through interstellar space for longer than stars will continue to burn. Your body would become part of a world that has no fixed address in the galaxy, no permanent stellar neighborhood, no stable gravitational relationships with anything larger than itself. The orbital mechanics of rogue moons create their own unique contribution to the death experience. These worlds follow hyperbolic trajectories through the galaxy, their paths determined by the gravitational kick that originally ejected them from their birth systems. Your death would occur on a world whose motion carries information about stellar encounters that happened millions or billions of years ago. The trajectory itself becomes a kind of fossil record, encoding in its mathematical parameters the story of the violent gravitational interaction that sent this world sailing into the cosmic dark. Your dying body would be carried along on a path that represents a direct physical connection to some ancient stellar catastrophe, making you a passenger on a world whose very motion tells a story of cosmic disruption. The timescales involved in these journeys stretch beyond human comprehension. Your rogue moon might complete a single orbit around the galactic center in 200 million years, during which entire evolutionary epochs would unfold on Earth. You'd be part of a world whose year encompasses the rise and fall of dominant species, the drift of continents, the cycling of ice ages and warm periods. The gravitational environment presents its own exotic challenges. Rogue moons exist in regions of space where the dominant gravitational influence comes not from any single massive object, but from the collective gravitational field of the galaxy itself. You'd be dying in a place where galactic mechanics operate with perfect clarity, unobscured by the gravitational interference of nearby stars or planets. These galactic tidal forces would be imperceptible to your dying nervous system, but they would subtly influence every aspect of your body's final transformation. The direction of galactic rotation, the gravitational gradients created by spiral arm density waves, the tidal effects of the galactic central black hole, all would contribute to the precise orientation and internal structure of your crystallizing remains. Your body would become a biological accelerometer, recording in its frozen tissues the subtle accelerations created by the galaxy's non-uniform gravitational field. Future gravitational archaeologists might be able to reconstruct the gravitational history of your death site's journey by analyzing the microscopic structural patterns preserved in your crystallized bones. The magnetic field environment in interstellar space creates phenomena that exist nowhere else we've encountered. The galactic magnetic field, weak but persistent across vast distances, would interact with the metallic components in your body in ways that create effects spanning multiple scales of physics simultaneously. The iron in your blood would align itself with field lines that stretch across light years of space, connecting you magnetically to star formation regions, supernova remnants, and other stellar magnetic phenomena scattered throughout your region of the galaxy. Your circulatory system would become a map of interstellar magnetic geography, preserving in its frozen architecture the magnetic landscape of your local galactic neighborhood. The radiation environment consists almost entirely of cosmic rays that have traveled for millions of years across the galaxy before encountering your dying form. These particles carry within them the nuclear signatures of stellar processes that occurred when the galaxy was in a different configuration, when different regions of space dominated star formation, when the cosmic chemical composition was measurably different from today. Some of the particles passing through your body might have originated in stellar explosions that occurred in other spiral arms of the galaxy, carrying information about nuclear processes that took place thousands of light years away and millions of years ago. Your death would be illuminated by radiation that connects you directly to the nuclear history of distant stellar populations. The chemical environment on rogue moons represents a unique intersection of primordial and process materials. These worlds carry with them chemical inventories that reflect their original formation environments, but modified by billions of years of cosmic ray bombardment and slow chemical evolution in the interstellar medium. Your body would introduce complex organic chemistry to surfaces that have been slowly accumulating interstellar dust for cosmic ages. The amino acids and proteins in your tissues would create chemical gradients in materials that have been shaped by processes operating on galactic timescales, introducing biological complexity to geological systems that operate according to stellar rather than planetary rhythms. The sublimation processes that distribute your organic molecules would operate so slowly that individual molecules might remain associated with your death site for millions of years before finally escaping to join the interstellar medium. You'd become the center of a gradually expanding cloud of biological chemistry, seeding interstellar space with complex organic compounds that could eventually be incorporated into forming star systems. The atmospheric conditions, where they exist at all, would consist of materials sublimating from surface ices at rates so slow they're measured in individual molecules per century. The weather on these worlds operates on timescales that make geological processes seem rapid, with atmospheric circulation patterns that might take millions of years to complete a single cycle. Your final breaths would contribute to atmospheric inventories so tenuous that each exhaled molecule might remain in the local atmosphere for thousands of years before escaping to interstellar space. You'd become a temporary contributor to meteorological processes that operate according to astronomical rather than atmospheric principles. The visual environment would present your dying eyes with the most spectacular and disturbing view possible, the entire galaxy spread across the sky in perfect clarity. Without any nearby star to create glare or local lighting effects, you'd see the Milky Way as it truly is, a vast spiral of stars and nebulae stretching across the cosmic dome. The view would be so clear, so detailed, that you might be able to make out individual star formation regions, supernova remnants, even the central bulge of the galaxy itself. Your death would unfold against a backdrop that encompasses the entire stellar population neighborhood, making of our cosmic you witness to the full scope of galactic architecture. But this spectacular view would also drive home the ultimate isolation of your situation. Every star you see would be unreachably distant, every nebula a monument to stellar processes occurring across impossible gulfs of space and time. You'd be dying with a perfect view of cosmic community while experiencing the most complete isolation possible in the physical universe. The geological context places your death among materials that have experienced the full range of galactic environmental conditions. The surface beneath your collapsing form might contain dust grains that originated in other star systems, cosmic ray spallation products created during the moon's journey through interstellar space, and impact materials from encounters with interstellar debris. Your impact with this cosmopolitan surface would add Earth-derived organic chemistry to a geological inventory that represents a cross-section of galactic materials science. The chemical signatures preserved in your impact crater future would provide investigators with information about biological processes occurring in a completely different stellar system, creating a kind of interstellar biology sample that records life processes from our solar system's particular corner of the galaxy. The preservation potential reaches theoretical maximums in these environments. Your body would achieve a state of chemical and physical stability that approaches the fundamental limits imposed by quantum mechanics and thermodynamics. Every molecule, every cellular structure, every neural pathway would be locked into crystalline configurations that could persist unchanged for periods measured in cosmic ages. Future explorers discovering your remains might find biological structures preserved with such fidelity that they could reconstruct not just your physiology, but potentially your individual genetic history, your lifetime exposure to various environmental factors, even the chemical signatures of the specific foods you consume during life. You'd become the most complete biological archive ever created. A perfect snapshot of human biology preserved in conditions that approach the theoretical limits of stability. The temporal framework of your death would operate according to galactic rather than stellar rhythms. Your preservation would span multiple galactic rotations, during which the stellar populations around you would evolve, new star systems would form and die, and the chemical composition of the interstellar medium would gradually change through ongoing stellar nucleosynthesis. You'd become part of processes that operate on the grandest scales possible in the physical universe. Your death site would participate in galactic evolution itself, witnessing and recording changes in stellar populations, chemical abundances, and even the large-scale structure of the galaxy as it evolves over cosmic time. The quantum mechanical effects dominating these extreme conditions would transform your body into something that exists at the intersection of biology and fundamental physics. Your tissues would exhibit quantum coherence effects normally confined to laboratory conditions, becoming a biological demonstration of quantum mechanics operating at macroscopic scales. The boundaries between your individual atoms would become blurred as quantum effects create coherent states spanning multiple molecules. You'd transition from being a classical biological system to becoming something that exists in quantum superposition, a state that challenges our fundamental understanding of what it means to be a discrete physical object. As we contemplate these ultimate expressions of cosmic death, we encounter the profound realization that we've moved beyond mere biology into realms where death becomes indistinguishable from transformation into fundamental cosmic phenomena. On these rogue moons, dying doesn't just end your story. It integrates you into processes that operate on the grandest scales in the known universe. You wouldn't simply cease to exist. You'd become part of galactic evolution itself, participating in processes that shape the chemical and physical development of entire stellar populations. Your death would transform you into something that bridges every scale of physical reality, from the quantum to the cosmic, from the temporal to the eternal. The rogue moons represent the ultimate frontier of death in our cosmic neighborhood, places where mortality transcends every boundary we use to define existence itself. Here, in the lonely spaces between stars, death reveals its true nature not as an ending, but as a transformation into something larger than biology, larger than chemistry, larger than individual existence itself. In these wandering worlds, we find the perfect expression of what it means to die on a cosmic scale, to become part of phenomena that connect us to the deepest structures of space and time, matter and energy, existence and eternity. Your death on a rogue moon would make you not just a casualty of exploration, but a participant in the ongoing evolution of the universe itself. The moons we've explored in our morbid survey represent more than exotic places to die. They are laboratories where the universe experiments with the fundamental limits of existence, testing grounds where the normal rules that govern life and death are pushed beyond their breaking points and into realms where new categories of being become necessary. Each world we visited has taught us something profound about the nature of mortality itself. Death, we've discovered, is not a simple biological process, but a transformation that can take forms so exotic they challenge our most basic assumptions about what it means to exist. From the gentle asphyxiation of Luna to the quantum crystallization of rogue moons, each death represents a unique interface between human biology and cosmic forces. But perhaps the most important lesson from our journey through these deadly worlds is what they reveal about the extraordinary nature of life itself. In cataloguing all the ways the universe can kill us, we've simultaneously discovered just how remarkable it is that we exist at all. Every breath we take, every heartbeat that sustains us, every thought that crosses our consciousness represents a victory against cosmic forces that operate according to principles utterly hostile to biological existence. The moons of our solar system stand as monuments to the creativity of physical forces, each one a unique solution to the problem of how matter organizes itself in the cold darkness of space. They are beautiful, ancient, complex, and utterly indifferent to the delicate chemistry that makes consciousness possible. Yet in their very alienness, they provide the perfect backdrop for appreciating the miracle of our own existence. As we conclude this exploration of cosmic mortality, we're left with a paradox that speaks to the deepest questions about life in the universe. The same forces that created these magnificent, deadly worlds also created the conditions that allowed life to emerge on Earth. The stellar nucleosynthesis that forged the heavy elements in our bodies also created the materials that compose these alien moons. The gravitational interactions that sculpted their surfaces also guided the formation of our own planet. We are connected to these distant, hostile worlds not just through the physics that governs both us and them, but through the fundamental realization that consciousness and cosmos are part of the same story. In contemplating death on alien moons, we're really contemplating our place in a universe that is simultaneously our cradle and our graveyard, our origin and our destination. The deaths we've explored exist not just as hypothetical scenarios, but as reminders of the incredible specificity of conditions required for life to exist and consciousness to emerge. Every exotic death we've catalogued serves to highlight just how perfectly calibrated our own world is for the delicate chemistry of biology. How precisely balanced the forces must be for atoms to organize themselves into patterns complex enough to contemplate their own existence. Our journey through the deadly moons of the solar system ultimately returns us to Earth with a renewed appreciation for the gentle embrace of our atmosphere, the protective shield of our magnetic field, the perfect distance from our star that keeps water liquid and chemistry active. We are not prisoners of our world, but beneficiaries of the most extraordinary cosmic coincidence, the alignment of forces that makes not just life possible, but consciousness inevitable. In the end, perhaps the most profound insight from our morbid tour is that death itself, in all its exotic cosmic forms, serves to define and illuminate life. Without the contrast provided by these alien worlds where existence becomes impossible, we might never fully appreciate the miracle of worlds where existence flourishes. The deadly moons of our solar system don't just show us how to die, they show us, by perfect contrast, what it truly means to be alive. The moons we've explored represent just the beginning of our cosmic catalogue of death. Each world has shown us that the universe doesn't simply kill through violence or extremes, but through the subtle art of making existence impossible. The gentle boiling of saliva on Luna, the diamond-hard crystallization on distant Sedna, the quantum coherence of rogue worlds, all demonstrate that death in space isn't just about dying. It's about transformation into something that transcends our understanding of what it means to be human. But there's something else happening in our survey that we haven't fully acknowledged yet. These deaths aren't random accidents of physics. They're expressions of fundamental principles that govern how matter and energy behave when pushed to their absolute limits. Each moon we've visited operates like a cosmic laboratory, testing different combinations of temperature, pressure, radiation, and chemistry. to see what happens when the delicate machinery of life encounters forces that operate on scales beyond biological comprehension. The patterns that emerge from our deadly tour reveal something profound about the architecture of reality itself. The way your body would crystallize on Europa isn't just a curiosity of extreme cold. It's a demonstration of how matter behaves when thermal energy drops below certain thresholds. The radiation-induced transformations on Io aren't simply exotic ways to die. They're examples of how high-energy physics reshapes the fundamental structure of organic molecules. What we're really exploring isn't death at all, but the boundary conditions of existence. These moons represent natural experiments in extremes, places where the normal rules that govern chemistry, biology, and consciousness are suspended and replaced by principles that operate according to different logical frameworks entirely. Your death on these worlds wouldn't just end your biological story. It would translate that story into languages written in physics, chemistry, and mathematics. Consider what this means for our understanding of life itself. If consciousness can be preserved in quantum crystalline structures, if biological information can be encoded in magnetic field alignments, if organic chemistry can be distributed across interstellar distances through sublimation processes, then the boundary between life and death becomes far more fluid than we've ever imagined. These exotic deaths suggest that information, pattern, and structure might persist in forms that we're only beginning to recognize as expressions of organized complexity. The temperature gradients we've encountered, from the molten surfaces of Io to the absolute zero approaches of rogue moons, represent more than just a spectrum of thermal environments. They're a catalogue of different states of matter, different regimes where the same atoms that compose your body would behave according to entirely different physical principles. The hydrogen in your cells would exhibit superfluid properties on some worlds, become metallic on others, and achieve quantum coherence on the coldest moons we've explored. This transformation of familiar elements into exotic states reveals something fundamental about the relationship between structure and function in biological systems. Your consciousness depends not just on the presence of certain atoms, but on those atoms behaving according to the specific physical principles that make neural computation possible. When those principles change, when matter begins to exhibit quantum rather than classical properties, the very definition of what constitutes a biological system must be reconsidered. The radiation environments we've catalogued tell their own story about the intersection of cosmic forces and biological architecture. The high-energy particles that would sterilize your tissues on some moons carry within them information about nuclear processes occurring throughout the galaxy. Your death by radiation wouldn't just destroy cellular structures, it would integrate you into the ongoing nuclear evolution of stellar populations scattered across thousands of light years. The magnetic field interactions that would align your iron-rich blood with galactic field lines represent something even more profound. These aren't just exotic physical effects, they're demonstrations of how biological systems can become connected to cosmic-scale phenomena. Your circulatory system would become a biological compass, oriented not toward magnetic north on some distant world, but toward the magnetic architecture that organizes matter and energy across interstellar distances. The chemical reactions that would redistribute your organic molecules across alien landscapes operate according to principles that blur the boundary between geology and biology. The sublimation processes that would spread your DNA across thousands of square miles of ice represent a form of biological reproduction that operates on geological timescales. You'd become the seed of chemical complexity on worlds that have known only simple molecular interactions for billions of years. But perhaps the most remarkable aspect of these cosmic deaths is their capacity to preserve information across timescales that dwarf every human conception of permanence. The crystalline matrices that would preserve your neural pathways on the coldest moons could maintain their structure for longer than stars continue to burn. Your thoughts, encoded in quantum-coherent ice crystals, might survive the heat death of the universe itself. And there we have it, our complete survey of every possible way to meet your end on the moons of our solar system. From Luna's gentle embrace of vacuum death to the quantum crystallization that awaits on rogue worlds drifting between the stars, we've explored over 200 different ways the universe has devised to transform human biology into something altogether more cosmic. What strikes me most about this journey isn't just the creative brutality of these alien environments, but what they reveal about the absolute miracle of your existence right here, right now. Every breath you're taking as you listen to this, every heartbeat pushing blood through your veins, every neural impulse firing in your brain represents a victory against cosmic forces that are actively hostile to the delicate chemistry of consciousness. These moons aren't trying to kill you. They're simply existing according to physical principles that make life impossible. The universe isn't malicious, it's indifferent. And that indifference makes our pale blue dot not a prison that confines us, but the rarest sanctuary in a cosmos filled with magnificent, deadly beauty. The next time you step outside and feel the gentle pressure of Earth's atmosphere against your skin, remember the methane lakes of Titan. When you watch the sun rise and feel its warmth on your face, think about those distant worlds where our star appears as nothing more than another point of light in an alien sky. When you take a deep breath of oxygen and nitrogen, consider that this simple act would be impossible on every single moon we've explored tonight. We are the universe becoming aware of itself, temporary arrangements of stardust that have learned to contemplate our own cosmic significance. And perhaps that's the most profound discovery of all. In cataloguing all the exotic ways to die among the moons of our solar system, we've simultaneously catalogued all the reasons why being alive on Earth is the most extraordinary thing that has ever happened in our cosmic neighborhood. Sweet dreams, fellow travelers in the cosmic dark. Tomorrow, you'll wake up on the only world in the known universe where consciousness can flourish, where life can contemplate its own existence, where beings made of stellar debris can look up at the night sky and wonder about their place among the stars. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.